In this video, I'm going to talk about the measure of association or correlation and its hypothesis testing. Okay, so in the elementary statistics, you found the correlation coefficient that measures the relationship between two variables. Okay, so or we also call association for the correlation. That also implies the measure of measuring the relationship between the two variables. So the graphical way of testing or checking the relationship between two variables is we do the scatter plot. We plot one of the two variables along x-axis and the other variable along y-axis. For example, the age in days and the wing length of 13 sparrows are given below. Data will be given in the another slide. So you see that along x-axis there is age, along y-axis there is length of the wings. So age is in days and the length is in centimeter. You see that whenever age is bigger and bigger and bigger, the values of the length is also bigger. So you can see that age and length are related to each other or associated to each other. Okay, also the scatter plot tells you the strengths of the association, how strongly they are associated or how strongly they are related. For example, if that points, the data points are along the straight line, we say that they are linearly dependent to each other or linearly associated. I would not say dependent, linearly associated to each other. Okay, or linearly related to each other, and that association is strong because they are almost in a straight line. Okay, if the data are a little far away from the straight line but still showing the increasing pattern, then you say that that will be weak association. But if there is no patterns of increasing or decreasing, then we say no association or no correlation. Okay, the scatter plot between two variables determines the type of association between the variables and the strength of association, usually drawn before finding the numerical value. We do the scatter plot before finding the correlation coefficient. Okay, so this is the plot of the data set given here. This is the data set. So X stands for the age of the sparrows in days from birth, and Y stands for length of the wings in centimeter. Okay, X and Y, and we plot X and Y along x-axis and y-axis, and this is the scatter plot for that. Okay, so association, it can measure, or the scatter plot can measure linear or non-linear association, meaning that if they are associated linearly or not linearly. Sounds like this data is associated linearly. So the data, they increase for some time and then decrease. So it is not linear. It is like curvilinear. You see that? It is like a curve, not a line, not a straight line. A very important thing about the association is, note that the association may not imply the causation. So sometimes it may imply, sometimes it may not imply. What does that mean? That means that length, in this example, length is the cause of the age. Whenever age increase, then the length is increased, right? So age causes the increase in the length. So increase in the age causes the increase in the length. But if you do the other way, the increase in the length does not cause the increase in the age, right? So there is association between length and age, but age is not caused by length. But the other way is true though here, right? Length is caused by the age based on this data. But this is not true all the time. It means that two variables are associated does not mean that one is causing the other one. Okay, it is not always true. Sometimes it may be true, but it is not always true. That's what it means. Scatter plot is not useful though to compare two data sets and cannot be used to conclude about population. What does that mean? That means if you have two different data sets, like two different scatter plot, then you cannot say which one is more associated or not, which one is not. So if there are two scatter plot, then it is hard to compare which one is more associated and which one is less associated. That's why the scatter plot is just a graphical techniques. Just usually it is drawn before you do the analysis, okay? The numerical, before you do the numerical finding, before you find the correlation coefficient. That's what you see in the elementary statistics, okay? But if you want to compare the two different scatter plots, it is hard. The numerical measure of linear association is correlation coefficient. If you want to find out what is the correlation coefficient, what is the coefficient of association from this data set, then this is the thing we find out. We call correlation coefficient. We denote the sample correlation coefficient by lowercase r. We call Pearson's correlation coefficient. And the population correlation coefficient is denoted by rho. We read that as rho, R-H-O, rho, okay? The formula to find out the sample correlation coefficient is n is the number of pairs, or you can say number of x values or number of y values. So n is the number of pairs times summation x and times y. So usually two variables will be given to you, y, x and y. So to find out the correlation coefficient manually, you need to find out x, you need to multiply x and y column and then find the sum of that. Similarly, find out the sum of x, sum of y, you multiply that by n, the first one by n. Also you need to find out sum of x squared and sum of y squared, and then plug in, find out these sums and then plug it into the formula. Okay, that's how you do manually. So the correlation coefficient, the sample correlation coefficient, lies always between -1 and +1, including -1 and +1. If r is close to +1 or -1, the association is strong. If r is close to 0, the association is weak. And r equals to 0, it means there is no association, okay? And to find out the correlation coefficient r, both variable must be metric or quantitative variable. Both variable must have numbers, otherwise you cannot do that. At least one of the variables should be normally distributed. Okay, that is another assumption you need. And let us do that example to find out the correlation coefficient on this data, okay? So the data is given in x and y, and I'm showing you how to do this by manually, okay? You need to find out x times y. You multiply 3 times 1.4, 4 times 1.5, 5 times 2.2, and so on. That is x times y. Also you need to find x squared, meaning you square x. 3 squared, 4 squared, 5 squared, and so on. And find out y squared. That is 1.4 squared, 1.5 squared, and so on. After you do that, you find out the sum of all these columns. N is 13. N is number of pairs, x and y. This is 1, 2, 3, and so on. So the total number of pairs will be 13. Sum of the x is 130. Sum of y is 44.4. Sum of xy is 14.8. Sum of x squared is 1562. Sum of y squared is 171.3. Now you plug in all these values here. N is 13 times summation xy is 14.8 minus 130 times 44.4 divided by that thing. Okay. So if you plug in there, you will get r equals to 0.9866, which indicates the strong positive association, because that r value is close to +1. So you see that strong positive linear association, because this formula is for the linear correlation coefficient. Okay, so the x and y, or you can say the age and the length of the wings, are strongly linearly associated to each other or related to each other. Okay, correlation coefficient is also called simple correlation coefficient, indicating that there are just two variables. Okay, so if there are more than two variables, we will do that later, but if there are only two variables, you can find out the correlation of x and y or y and x. You will get the same thing. Okay, x and y or y and x will be the same thing. All right, so I think I have done this problem here in R. I copied the age data, I copied the length data, I plotted the age versus the length. You see that? Age comma length plot. This is what we got. Okay, this is what we got there. Now I am trying to write that age and length in the column format, and then I want to name the age by x. I'm writing data.frame. Inside the parenthesis, x equals to age and y equals to length. That's what I did. That will put the x and y in the column format. Okay. The next column I am creating on table 1 is x times y, which is age times the length. Okay. Similarly, table 1 x square, that's why I'm naming it, is age square, and table 1 y square will be length square. And then let me run all those and then see the table 1. This is what I exactly got, the same thing here. Now you can find out the summation of that, and so on. Okay, and after you find out the sum of all the columns, how do you find out the sum of columns? So you can do column sums, right? And then table 1, if you do that, what do you get? You get, let me run that. Oh, the uppercase T, right? Uppercase table 1. To do that, you will get, see, sum of x is 130, sum of y is 44.4, summation of x times y is that, summation of x squared, summation of y squared. So that's what I noted here, and then you plug in into the formula. Okay, that's what you do. Now, if you want to do directly by R, but be careful that you need to enter the x and y though, age and length, and then you do COR and then age comma length. That will imply Pearson's correlation coefficient. Okay, that's just a one-line code after you enter the data. Correlation age comma length. That's what you do. Okay, if you do that, you get 0.9866. That's what you get. R equals to 0.9866. So R is almost 1, so a strong positive association. Okay, so the next thing that I want to talk here is hypothesis testing. How do you test the hypothesis? Because whenever you find out the correlation coefficient, that is the sample correlation coefficient. That's what we found, lowercase r, right? So one of the main goal of the statistic is you find some findings from sample and you apply that into the population, right? So you want to test the hypothesis in the population, but you want to use the findings or statistic from the sample. That's what it says. The hypothesis testing about correlation coefficient. Test if there is a linear association between two variables in population or not. The assumption is for simple correlation coefficient, no assumptions needed, but for hypothesis testing, we need these 4 assumptions. One is the normality. Both population must be approximately normally distributed. Another is the homocysticity. That means for each value of x and y values have the equal variance. We will talk about that, what that means, okay? Because x values can be repeated or y values can be repeated. So for each x values, if they are repeated for each x values, the y values must be equally scattered from the center values. That's what it is saying. Okay, and similarly for the y values. Linearity is another assumption, that is the linear association between x and y. And the continuity is both x and y must be continuous variable and there should not be any outliers. Okay, so what are the steps for the hypothesis testing? Step number 1, the null and alternative hypothesis. The null hypothesis is rho equals to 0. What that means? That means the population correlation coefficient is 0, meaning there is no association between the two variables in the population. Versus the alternative hypothesis is rho not equals to 0, meaning the population correlation coefficient is not 0, meaning the two populations are related to each other or associated to each other. Step number 2, find the correlation coefficient R from the sample and find the test value. This is the formula to find out the test value. R under the root n minus 2 over 1 minus r square. Step number 3, find the critical value or p-value. For critical value, use two-tailed t-test with n minus 2 degrees of freedom. For the p-value, you do 2 times pt, t comma n minus 2. This is for the left tail test, or how this will be always right tail. This, if t is negative, this is the formula you use to find out the p-value. If t is positive, then you will have to find out the area right of the test value, right? So you need to do 1 minus pt, 2 times 1 minus pt, and then t comma n minus 2, where t is the test value from step number 2. And step number 4 is reject the H0 if test value falls within the critical region or if p-value is less than alpha. And step number 5 is summarize the result. So the rule of thumb is, if you have value R but no confidence interval or p-value, reject H0. That means say that the correlation coefficient is not 0, meaning the population variable are related to each other if R is greater than 2 over root n. Usually if R is greater than 2 over root n, your conclusion or the decision of the hypothesis testing will be reject H0. Okay. So this is the so next thing I am going to do is, here you see that our null hypothesis is rho equals to 0 versus rho not equals to 0, meaning there is no correlation or association versus there is association between two population variables, right? But sometimes if you need to test for H0, rho equals to certain value versus rho not equals to that value or greater than or less than, then we don't use the above method. The method we just use, we will not use that. In that case, we need to find out the g value. Okay, that's the critical value we find out, g minus zeta 0 over sigma g. What is g, what is zeta 0, what is sigma g? Given by this formula. G equals to 0.5 natural log of 1 plus r over 1 minus r, where r is the sample correlation coefficient. Zeta 0 is 0.5 times natural log of 1 plus rho 0. What is rho 0? Rho 0 will be that value. Okay. If rho 0 is 0, that zeta 0 will be 0. So that's why we are not using that value, right? Rho 0 will be not 0. And then use that. And sigma g is 1 over n minus 3 under the root, where n is the number of pairs. That's the formula you will be using if your null hypothesis doesn't have rho equals to 0 versus rho not equals to 0. So next is the confidence interval for population correlation coefficient. For the confidence interval, we use this formula. So lower bound and upper bound. Lower bound is given by this formula and upper bound is given by that formula. So LB equals to 1 plus f sub alpha times r plus 1 minus f times alpha, and divide by that, and UB is that, where f sub alpha is the f value from the f table with two-sided alpha, okay, and we do n minus 2 comma n minus 2 will be the degrees of freedom, because whenever you find out the f value, you need the 2 degrees of freedom, right? One for the numerator, another for the denominator. You will be using n minus 2 in that case, okay. So there is a homework problem, I will ask that, but before that, what I'm going to do here is, let's see what I have. So I want to show you what will be the hypothesis testing, because we just see that in the sample, right? in case of the sample correlation coefficient is 0.98, which is close to 1. So it says that the two sample variables have a strong positive linear association. But we cannot tell anything with the correlation coefficient only. We cannot tell anything about the population variables, right? So we need to do the correlation hypothesis test on the correlation hypothesis test. Okay. So if you want to do that for this problem, what you do is basically, let me look at this. I'm just naming it as result 1, which is equals to the hypothesis testing. The direct hypothesis testing is the function is core.test. That is the correlation test. Age is one variable and length is the other variable. Okay, age comma length. Method equals to Pearson. That's what we are using here. And confidence level is 0.95. Let me run this and then run the result. This is what I got. See, the sample correlation coefficient we found is 0.9866. That's what we used. And then there are two different methods. Okay, one is the t-value method. Another is the method that we used here. The p-value method, or the critical value method, right? So here that's the test statistic. That's what you get, the test statistic. Degrees of freedom. P-value is very small. So p-value is small means what? We reject the null hypothesis. You see that? Meaning that there is association between x and y. Because reject the null hypothesis, because the null hypothesis was rho equals to 0, meaning there is no association between the population variable x and y, right? So here we found that there is, so because we got p-value is less than alpha, so p is less than alpha, we reject it 0. That means there is association between age and wing length, right, of sparrows. That's what you get. Okay, all right. So how do we find out? Let's see. So this one has the comparing two correlation coefficients. Okay, how do I compare the two correlation coefficients? These are the steps. Number 1, rho 1 equals to rho 2 is the H0 versus rho 1 not equals to rho 2. The test statistic is T equals G1 minus G2 over sigma sub G1 minus G2, where G1 is 0.5, 1 plus R1 over 1 minus R1. G2 will be that I will be replaced by 2, 0.5 natural log of 1 plus R2 over 1 minus R2, and I equals to 1 and 2. And the sigma, it is the error term, is sigma G1 minus G2 is given by 1 over n1 minus 3 plus 1 over n2 minus 3 whole root. And the critical value is depending on the tails, we find out the G alpha 2, that is the normal from the normal distribution, right? Because the G is the standard normal curve. Okay, so that's the critical value we find out, and then we do the decision and conclusion. So you can actually find out the p-value too. So p-value will be the area right of the test value or the area left of the test value, right? Depending on what you get for the test value. If you get negative, you do 2 times area left. If you get positive, you do 2 times area right of the test statistic. Okay, let us do one example here. For a sample of 98 birds, wings and tail lengths. So you are taking a sample of 98 birds and they have the measurement of wing and tail length. So there are 98 pairs of data, right? So suppose that R, the sample correlation coefficient, is 0.78. A sample of 95 such measurements from a second bird species yielded that the sample correlation coefficient is 0.84. Test whether the two correlation coefficients are equal or not. So we want to see that if both species are have the same type of association or not. See, you can compare. If you do numerically, you can basically if you do the numerically and if you do the hypothesis testing, you can basically compare the association between the two different scatter plot. That's what we're doing here, right? So test whether the two correlation coefficients are equal or not in their population with alpha equals to 0.05. So the H0 is rho 1 equals to rho 2 versus rho 1 not equals to rho 2. Test value is G1 is 1.0454. You use that. And then G2 is that. N1 is 98, N2 is 95, sigma is 0.1. Just use that formula, right? So the test value is negative 1.202. Now the critical value will be for 0.05 and two-tailed test, the critical value will be 1.96. But if you find out the p value, then 2 times p norm area left of the test value, area left of this value. So p norm and then just use that value, comma 0, comma 1. So what do you get the p value? We'll see. And we will get p value less than alpha. That's why we do not reject the null hypothesis. So basically how I got these numbers, I did here. N1 is given, R1 is given, N2, R2 are given. So G1 is 0.5 times natural log of that thing, right? So see, in R, the natural log is basically log, like that. And then you let me run all these. And G1 is that much, and G2 is also found using that formula. Sigma G also finding using that formula, okay? That is sigma G. What is the test value? Test value is G1 minus G2 over sigma G. That's what I did. Test value. So that is the value of T. Now I want to find out the p value. P value is, because the test value is negative, right? So the p value will be 2 times area left of the test value. That's what I got. So the p value is 0.22941, which is greater than alpha. P value is greater than alpha. Hence, do not reject the null hypothesis, meaning that those two correlation coefficients are equal in the populations, okay? Or the association between those two pairs of populations are equal. That's what we say. Let us talk about the note. Since these two populations have the same correlation coefficient, we find their common correlation coefficient using GW equals to N1 minus 3 times G1 plus N2 minus 3 times G2 over N1 plus N2 minus 6. What does that mean? That means because you see that when we did the hypothesis testing, we say that we do not reject the null hypothesis. Do not reject the null hypothesis means rho 1 and rho 2 are equal, right? So rho 1 and rho 2 are equal means both of those pairs have the equal correlation coefficient. So if you combine those two populations together, right? For example, let's say population 1, population 2, population 3, population 4. If you combine population 1 and population 2, population 3 and population 2 and population 4, then in the combined, then you see the correlation coefficient in the combined format will be, so we can find their common correlation coefficient using, this should be using G sub W equals to N1 minus 3 times G1 plus N2 minus 3 times G2 N divided by N1 plus N2 minus 6. And then we solve GW equals to that. So first of all, you find out GW using that. And then use that GW here and then solve for RW. That will be the common weight correlation, R sub W. Okay. The next one is comparing multiple correlations. So we saw how to compare the two correlation coefficient. Okay. So if you need to compare multiple correlation coefficient, I have done one here. Then the null hypothesis will be rho 1 equals to rho 2 equals to rho 3. So all those populations have the equal correlation coefficients. versus not all the row i's are equal, right? And the test statistic is given by, first you need to find out Ri, meaning the correlation coefficient between each of those populations. If there are 5 populations, you do the correlation coefficient of 1 and 2, 1 and 3, 1 and 4, 1 and 5. Similarly, 2 and 3, 2 and 4, 2 and 5, 3 and 4, 3 and 5, and 4 and 5, like that. Okay, those population. First we find out Ri, and also we find out Gi using the same formula we used before, and then we use chi-square equals to Ni minus 3. Ni means so the size of the samples, right? Minus 3 squared, minus 3 times Gi squared, Gi is that, minus summation of Ni minus 3 times Gi whole square divided by summation Ni minus 3. This is the chi-square value. Now the critical value will be, that's the test value. So critical value will be depending on alpha 2-tail. We use chi-square table to find out chi-square alpha k minus 1, where k is the number of populations which row I are to be compared, and then we make the decision. Okay, so I'll show you how to do that by R directly. If H0 is not rejected, then we find the common correlation coefficient using the same technique there, summation Ni minus 3 times Gi over summation of Ni minus 3, and then find out the corresponding Rw using that GW value here in this formula. Next is, we can perform multiple comparisons among the correlation coefficient using 2K type method, which computes the correlation coefficient of each sample versus other. Okay, and see the lab 10 file. Let me show you that. So to run this multiple correlation coefficient, you need to install a package called Psych, P-S-Y-C-H. Install that package is Psych. I think I have installed that already, so I will just run the library here. Now data is empty cars. So what types of data is that? You may not know that. Okay, let me do that. So empty, what type of data is that? See, it has many types of cars and models. Okay, and then you have, for each of these models of the cars, you have so many variables here: mile per gallon, cylinder size, displacement, horsepower, all those, weight, and a gear, all these. Okay, now what we want to do is, we want to test if there are relation between these or this or this or this, like that. Okay, so first of all, let us figure out which one are the quantitative data. So mile per gallon is quantitative data. Cylinder is, you can think of this as a qualitative, because it just counts the number of cylinder. Okay, displacement, it is numerical. So I am picking the numerical data, selecting only the few columns that are numerical. So what I am doing here is, I am collecting all the rows of these columns that are numerical only. That's what I am doing, and I am naming it as my data. So these are the only numerical data I collected, or I imported, or I loaded from that data set. Okay, now what I am doing here is, result 1 equals to correlation of my data. Let us look at that. So what is that? What does that mean? That means, look at that, it found the correlation between all these columns. You see that? What is the correlation between MPG and displacement, MPG and HP, MPG and DRAT, MPG and WT, MPG and QC? So how do I read this? Is, look at this, MPG and MPG is correlation coefficient is 1. MPG and displacement correlation coefficient is negative 84, negative 0.84. That means if you increase for bigger values of MPG, displacement will be smaller. Okay. Similarly, MPG and HP, the correlation coefficient is this. MPG and DRAT correlation coefficient is like that. MPG and weight correlation coefficient is that. Similarly, you find out the displacement and MPG is that. So see, this value and that value are the same, because that is the the correlation coefficient, coefficient of association between displacement and MPG. So either way, it doesn't matter which one you take first, you will get the same correlation coefficient. So this will present correlation coefficient that way. Okay. So next is, I want to, since all these are given in many, like 7, 8 decimals. What I'm going to do here is I'm rounding the result one with 2 decimal places only. You see that? So HP and MPG negatively associated. MPG and DRAT negatively associated. So you can find out any of those combinations. Now what I want to do is I want to plot all these, okay, as well as I want to test the hypothesis for each of those, whether MPG and displacement are correlated in the population or not. MPG and HP are correlated in population or not. So I'm going to do that. Okay, this is the code on line 48. That's what you do. Now these are the R values that we got already. The P values are this. So P value significant means a P value less than alpha means we reject the null hypothesis, meaning that those two variables are correlated. Okay. You can basically round it and then check, but still it is okay. So displacement and MPG are correlated because the P value is less than alpha. So all these, almost all these are correlated to each other, right? Which are not correlated is, let me see if there is any that is not correlated. So this one, right? This one will be 0.06. This one is 0.06. This one is 0.03. Like that. Almost all other than those are the correlated because it is 0.06, right? So that decimal, because of the negative one, that decimal goes 1 unit to the left. Okay. So this is what we got. Okay. Similarly, look at this. So DRAT and QSEC are not significant because these are the P value are greater than alpha. Greater than alpha on this. So they are not significant. So you read like that. Okay. Now, if you want to plot all those correlation in a nice plot, how do you do that? Look at this. You need to install a package called Performance Analytics. Okay. First of all, you need to install this by commenting that and run that and then comment that. Let me do the library and then my data is my data. Now I'm doing the chart. Look at this. What is that chart stand for? So this one, this column is for MPG. This column is for displacement. This column is for HP, horsepower, DRAT, weight, QSEC, like that. If you look at this is the plot. This is the histogram for the MPG. You see that it is almost, you can say, it is okay, it is normal, kind of. It says the normality, checks the normality as well. And this is the scatter plot of MPG and displacement. Okay, scatter plot of MPG and displacement. Now this value is the correlation coefficient between MPG and displacement. You see, like that. So that's what we got for MPG and displacement. If you want to see the MPG and, let's say, horsepower, where is the horsepower? This is the horsepower. So MPG and horsepower have the correlation coefficient negative 0.78, which is significant. It is star, that means it is significant. Okay, P value will be less than alpha. And then what is the scatter plot look like? Go here. This one is the scatter plot for MPG and HP. Okay, so in this way you can see the scatter plot, the population distribution of each variable, scatter plot, and the P value and R value. Okay, R value is that, P value is significant because 3 stars means for 0.001 it is significant. Okay, I think 0.005, I guess. Let me check, because it says whenever you do the let me show you what that star means. Okay, it doesn't show the star here, but again, you see, oh, there you go. Look at that. P-value 0.0, for 0 there will be 3 stars. For 0.001 there will be 2 stars. For 0.01 there will be stars. For 0.05 there will be just dot, and for 0.1 there will be nothing, just blank. Okay, that's what it is saying. You can look at the comment that I commented here. What it says here is, look at this. The distribution of each variable is shown in the diagonal. That is the distribution of each variable in the diagonal. On the bottom of the diagonal, the bivariate scatter plot with a fitted line are displayed. See, this one, for example, is for displacement and MPG. This is X versus Y scatter plot. For HP, this one is for HP and displacement, and this one is for HP and MPG scatter plot. Okay, and so on. On the top of the diagonal, the value of the correlation plus the significant level as stars. These are the correlation coefficient on the top of the diagonal for each of those, right? And then 3 star means it is significant with p-value almost 0. 2 star means p-value almost 0.001. 1 star is 0.01, and then dot is 0.05, and so on. Okay, so I think that's all I wanted to say here. Okay, so next time we will talk about the non-parametric test for the correlation coefficient. Okay, thank you guys.